in both models, remember I suppress X, this age and gender are treated as X. This is the result. Good job. Okay, so I select just display a few SNPs here. 1, 3, those are somewhat spatial here. This gamma 0, gamma 1, remember this is the factor that will affect our correction. Okay? So the larger this factor is, the more likely the bias will be need to be correct. So those are somewhat big here. Okay? So for test 1, basically we assume we have very sparse outline, which is not true. For test 2, we use 10% baseline prevalence rate. This is close because the case we select from the population was top 10%. Okay? Case 3 here, 20% for 30%, 0. This last one is a Bayesian approach. We assume the true center here and a variance here, true mean here and the variance here. Okay, so those displayed are p-values here. If you look at this p-value here, this is in this particular study is close to the truth because we know the sample 10%, top 10% in the population. So this is close to the truth. Okay? But now this is significant. Okay? So why I display the other p-values? I want to show you that if you change the prevalence rate, then this significance can change for some of those substantially, for others relatively insignificant. Okay. For this one, you see that if you change from test 2 to 3, then the p-value can be substantially low. Okay. So when you have this kind of analysis results, we can interpret this based on our knowledge on the prevalence rate, which usually is not quite accurate. Okay. This is the summary of this analysis. Here, we do not see any SNPs in this analysis for this example that achieves statistic significance, even at 5% nominal error level. Okay. What does that mean? Basically, we have two interpretations to one pair. We would like to mention here. The first one is that we have examined mostly the SNPs that are associated with high-density lipid protein. Those genes regulate the low-density lipid protein may be different from those regulate the high-density lipid protein. Okay? If that's the case, that means the association with different genes. We only concentrated those SNPs that had observed higher level of association with the high-density lipid protein. Okay? The other one could be that you do not have a very large sample size since it's a secondary phenotype. The sample size cannot be somewhat equivalent to the case control sample size. Okay? If this low-level lipid protein prevalence rate is say relatively rare, then your sample will capture relatively low rate of extreme case. In that case, it is likely you have relatively small number of cases. So that's why you don't observe the significance. Basically, in the end, it means the sample size is too small for the second treatment. Okay? This is a summary of the proposed approach. The good side of the approach. Okay? One thing is I like this approach because it gives us a explicitly correction formula to use it is very easy, condensed, that you can apply very easily. And when you use this condensed explicit formula to correct the bias, then you can perform lots of statistical analysis because of the explicit function form you have. The other thing is that computationally, this correction approach is very efficient. You can do just only two regression analysis and then leave the data and play with the results. Okay. This correction approach, I use this for logistic regression for this particular example. Actually, it is very general. Okay, it can be applied to all kinds of outcomes. Here, I show you just binary outcomes. It's okay if you have quantitative outcome. The correction result is the same. And also, there is a particular thing I would like to mention. If you have secondary primary outcome, which is continuous, if you use normal model, actually this correction result is exact. There's no correction. Exact function form should hold. Okay. So for continuous outcome, modeled by normal linear model, the correction is actually not approximate, exact. And also, it can be used to correct similar bias in family-based solution study. Of course, in that situation, the model itself becomes more involved, but the principle and the method can be easily extended to that kind of situation. In fact, any kinds of generalized linear model, you can do that. Okay? So it's very, very general approach. It's not restricted to logistic regression model, which we have here. And also, we can improve this correction approach by higher order approximation. But if you do that, then the formula is not that simple. Okay. There's some future works. Actually, we have done some of these things. Okay. Thanks for your attention.